We're going to continue looking at some specific forces and talk about inclined planes here. Now, this isn't technically a new force, but it is a new situation. There's going to be a little bit of a trick that we're going to use when we're analyzing these problems. So let's take a look for a second at the forces that are going to be acting on an object when it's on an inclined plane. And this could be a ramp, a hill, really anything that's sloped is going to count as an inclined plane. So the forces we're of course going to have the force of gravity going straight down. We're going to have our normal force, which now is going perpendicular to our incline. And then let's say it's maybe being pulled up the incline with some pulling force, and there is friction going back down the incline. So if we look at those forces, okay, we're thinking about our normal coordinate system. This force is not horizontal, it's going to be up at an angle. This force is at an angle, that normal force, and that force of friction is at an angle. Something else to keep in mind, let's say we're accelerating it up the incline. Our acceleration is going to look something like that, which also is at an angle. It's neither purely in the x or purely in the y direction. So the trick we're going to use here is we're going to tilt our axis. We're going to take our normal x and y and rotate them so our x direction is now parallel to our inclined plane and our y direction is now perpendicular. And that means that the pulling force is now in the x direction, the force of friction is now in the x direction, the normal force is now in the y direction, and our acceleration is now purely in the x direction. The only thing that screws up is that force of gravity. So we now need to do our components of the force of gravity. So we're going to have one component going perpendicular to the incline like this, one component going parallel to the incline like that. So that is our new method, or our new little trick for dealing with an inclined plane. What ends up happening is that whatever the angle is of the incline down here, that ends up being this angle, that upper angle in our triangle showing the components of the force of gravity. So the y component ends up being Fg cosine of theta, and the x component ends up being Fg sine of theta. So that's going to be our basic setup. Other than that, inclined planes really aren't anything different. There's really nothing new, just this little trick about rotating our axes. A few quick tips here with inclined planes. The first thing, like we just talked about, is we want to always tilt our axis. That's really the most important tip that I can give you here for solving these problems. The next tip I can give you is be careful with your angle. When you're doing those components of gravity, you don't want to switch sine and cosine. So gravity, as we saw in the last diagram, is going straight down, and when we do our components, we have our one parallel and our one perpendicular, and the angle of the incline will always be this upper angle here. So what will always happen if we know that angle of the incline is this y component that's perpendicular to the incline will always be cosine, and this x component will always be sine. So we do know that for sure, assuming we know this angle relative to the horizontal. And then the last thing is we're solving this just like a regular force problem, which means good old max and may are coming into play. We're drawing a free body diagram each time. All those things that we always do when we're solving a force problem. Let's go ahead and try a practice problem here. So I'm going to first draw my free body diagram showing all the forces acting on this object. And when we're doing these inclined ones, we're going to draw it on the incline. That's slightly exaggerated, slightly more than 11 degrees, but that's okay. So the forces we of course have gravity acting straight down. We know that one's always going to be there. We have our normal force acting perpendicular to our incline, and it says we're pushing this shopping cart up the incline. So we're going to have a pushing force going up the incline like that. Keeping in mind that our new x-axis looks like that and our y-axis looks like that. We're going to break it into our x and y components. So the y is going to look like that. Keeping in mind that that's perpendicular to the incline, and the x is going to be going down at an angle. It should be parallel to our incline. It's not drawn directly to the left, as sometimes people will do it. And we know that then this upper angle here is 11 degrees. Breaking these into our components, this y component is going to be Fg cosine of 11 because it's the adjacent side, and the x will be FG sine of 11. We can now go ahead and set up our max and our may here. So I'm going to start with my max. So in the x direction, the forces we have our FP, that pushing force, minus FG sine of 11, and that's going to be equal to m times AX. I am keeping in mind here that my acceleration is going up the incline, and it tells us it has a value of 0.7 meters per second squared. So continuing on from here, filling in what I know, I'm looking for FP. FG I know is just mg, so I'm going to fill that in. And that's going to be equal to my mass, which is 45 times 0.7. So I have FP minus 45 times 9.8 times sine of 11. And doing the math here, that's going to be equal to 31.5. And then when I solve for FP, I get that my pushing force here needs to be 115.6 newtons. And that's going to make it accelerate up the incline here at 0.7 meters per second squared. Moving on to my next one, I have a child sliding down a muddy hill after a rainstorm. And we want to know the acceleration of the child, so we'll start once again with our free body diagram. There's my hill, here's my object, and so I have the force of gravity. I have my normal force, and if they're going down the hill, right, our acceleration is going to be down like that. Friction is going to be going up the hill, kinetic in this case. My angle here is going to be 19 degrees, and I can go ahead and draw my x and y components for gravity. And so this y component will be FG cosine of 19, and my x component will be FG sine of 19. So I'm going to go ahead and set up my max and my may here. So in the x direction, I have FG sine of 19 minus FF equals MAX. And I'm just making down the incline be the positive direction since that's the way that our acceleration is going. In the y direction, we're going to have our normal force minus FG cosine of 19, and that's going to be equal to mass times 0, because once again, much like a lot of these friction problems on level surfaces, we are not accelerating perpendicular, okay, to that incline in the y direction. So that means our y acceleration is 0. What I can say then is that my normal force is going to be equal to that FG cosine of 19, and I'm going to sub in mg for FG. And so that's the value of my normal force. I know I don't have any numbers here other than the angle, but that's still useful information. When I go over to my x side, I'm going to sub in for force of gravity there as well. And my normal force I know is going to be mu k times Fn. That's going to be equal to m times Ax. And I can substitute in that normal force I just found, so I get mg sine of 19 minus mu, which I actually know, but I'll leave it as mu for now, times mg cosine of 19 equals MAX. And here's what I can do, and this works out really nicely. I can now divide out an m. Be careful, okay? You need to have an m in every single term, okay? And I know some people will say, well, there's two m's on this side and only one on that one. How does it cancel? What we're really doing here, all right, mathematically, is we're really factoring out an m. We're saying m times g sine 19 minus mu g cosine 19, and then dividing out that m. That's why it works. We actually have to have the m in both terms in order to be able to divide it out. We can't cancel the m in this step here. Right, so be careful with that. Mathematically, that's something that throws people off a little bit. Now that I have this, I have everything I need, and I can actually go ahead and solve for my acceleration. So what I'm going to have here is 9.8 sine of 19 minus 0.2 times 9.8 times cosine of 19 equals ax. And so I find that my x acceleration here is 1.34 meters per second squared. One last problem here. We have a snowboarder going down a mountain at a constant speed, and we want to know what the angle of the incline is here. So I'm going to set up my forces once again, leave that angle as a theta. We know we have the force of gravity and the normal force, and in this case we have a coefficient of friction, so there must be a force of friction. Don't see any mention of any other forces, so that's it for now. Break gravity into my x and y components as always, so my y is Fg cosine of theta, and my x is Fg sine of theta. And I'll go ahead and set up max and may. So in the x direction, we're going to have this Fg sine of theta minus the force of friction equals max. And in the y direction, we're going to have Fn minus Fg cosine of theta equals may. Now we know in the y direction we're not accelerating perpendicular to our incline, so we can say that this goes to 0, and my normal force is simply equal to mg cosine of theta. In the x direction, it also happens to be 0, but for a different reason. It tells us that we're sliding down this hill at a constant speed, so that means there is no acceleration in either direction in this case. So I can say that mg sine of theta is equal to my force of friction, which is simply mu times my normal force. I'll go ahead and substitute in for my normal force here that I just found using my may. And so we can say that mg sine of theta equals mu times mg cosine of theta. Here my masses cancel out, as do the acceleration due to gravity, and I'm simply left with sine of theta equals mu k times cosine of theta. Now, you might remember a little trick that you learned in trig class for this one, maybe not, but there is a really nice way of solving this, and it relies on this identity, and the identity is that sine of theta divided by cosine of theta is equal to tangent of theta. So whenever I see a sine of theta and a cosine of theta, I'm always thinking in my head, I'm going to need to eventually divide them and turn them into tangent of theta. We have a theta on both sides, and we somehow need to combine them and get down to one single theta. So the way I do that is by dividing. So I'm going to divide both sides by cosine of theta. So I can say sine of theta over cosine of theta equals my coefficient of kinetic friction. And that means that tangent of theta is equal to my coefficient of kinetic friction. If I want to go ahead now and solve for theta, I'm just doing some inverse trig here. And so I can say that theta is simply equal to the inverse tangent of mu k. And there I have my answer. So as we just saw in the last problem, there is this nice little identity. Sine of theta divided by cosine of theta equals tangent of theta. And so that's a nice way of combining those two into a single term with theta in it, which is what you're going to want to do if you ever have both sine of theta and cosine of theta in your problem and you don't know theta. All right, so that's just a nice little trick to keep in the back of your mind.